Hi, and welcome to the Matter, Energy, and Nutrition video lesson. So we're going to begin by talking about matter, and matter is classified into both pure substances as well as mixtures. So pure substances is further broken down into elements and compounds, while mixtures is broken down into homogeneous and heterogeneous. And we're going to talk about each of these subsets momentarily. Elements are composed of a single type of atom. We have a list of the elements on the periodic table. All 100 and something elements are listed there. And elements are composed, like I said, of a single type of atom. So if we look at this sample of copper, each one of these spheres represents an identical copper atom. Compounds, on the other hand, contain two or more elements that are going to be chemically combined in a fixed ratio. And so NaCl is table salt. That's going to be 1 sodium combining with 1 chlorine, or that's our ratio, 1 to 1. And water is 2 hydrogens per 1 oxygen. And each one of these water molecules is identical, H2O, another H2O, another H2O. And so again, the elements are chemically combined in a fixed ratio. The interesting thing about compounds is that the compound actually has completely different properties than the elements. So table salt, NaCl, is a delicious white crystalline compound, whereas sodium in its elemental form is a very soft metal. It's got a similar consistency to like a sharp cheddar cheese. You can actually cut it with a knife. It's very soft metal, and it explodes when it touches water. Over here we have chlorine gas, and chlorine gas is a toxic green gas. It was used in both world wars actually as a warfare gas. Very, very nasty stuff, very poisonous. And we have this metal that explodes when it touches water, and this poisonous gas, neither of which we'd want to put in our mouth, but when we combine them and react them with each other to make a compound, the compound's got completely new properties. So moving on to mixtures, homogeneous mixtures are uniform throughout, and I like to think about them as the components dissolve into each other. And they give the example here of brass being a homogeneous mixture. And so we have the zinc atoms dissolved into the copper atoms to form this new solution, this brass solution, this brass homogeneous mixture. Another example would be like sugar water or salt water. The components dissolve into each other. Heterogeneous mixtures, on the other hand, these components do not dissolve into each other. And so oftentimes people use food examples like pizza or a cheeseburger or a tossed salad. We have these different components that are separate from each other. They give the example of pennies and water right here. And so the pennies don't dissolve in the water, and the composition's not uniform throughout. So let's try and identify these as elements, compounds, heterogeneous mixtures, or homogeneous mixtures. So let's start out with pasta and tomato sauce. Well, pasta and tomato sauce, those don't dissolve into each other. And so this would be an example of a heterogeneous mixture. Right here we have aluminum foil. Aluminum foil is made of aluminum. Aluminum is an element. We know that because it's listed on the periodic table. So this is an element right here. Carbon dioxide is an example of a compound. Carbon dioxide is made of CO2 molecules, and so we have those elements chemically combined in a fixed ratio, 1 carbon per 2 oxygens. And then finally, air is an example of a homogeneous mixture. So in the air we have oxygen and nitrogen and a number of other gases dissolved into each other. So I'd like you to now pause this video and then complete question number 1 on the activity. Alright, let's move on and talk about energy. So energy comes in two forms. We have what's known as potential energy, which is energy that's stored. And so we see this take various forms. So water behind a dam would be an example of potential energy. A compressed spring is also potential energy. But where do we see it in chemistry? Well, we see it actually stored in bonds. So for instance, gasoline has stored energy in it. We know that we can burn it. It gets really hot. We can power cars. Coal is similar, so fossil fuels in general have a lot of potential energy stored in them. But food does also, and so food has potential energy. That stored energy is what fuels our body. And our other form of energy is what's known as kinetic energy, and this is energy of motion. So this could be like water flowing over a dam, the motion of working out, a car traveling down a freeway, burning gasoline to release heat. And so heat is another example of kinetic energy. And heat's the primary form of kinetic energy we study in chemistry. So energy has a few different units associated with it. One unit is going to be joules, and another unit is going to be calories. And so these are both commonly used, and the exact ratio between these is that there is 4.184 joules for every 1 calorie. And so we can set up our conversion factors here if we wish, converting from this case we could cancel out calories to make joules, and over here we could cancel out joules to get calories. Just pick the proper ratio to get the unit cancellation we're seeking. And it's a bit confusing. We actually have two different types of calories. We have calories with an uppercase C. These are sometimes called big calories or food calories. And these are actually equal to a kilocalorie or 1,000 of these little calories right here. So pay very close attention because calories with an uppercase C and a lowercase c are actually different units. And with uppercase C, it's actually 1,000 of these calories with a lowercase c. And similarly, every 1 kilojoule equals 1,000 joules. So we have an example problem right here. We want to figure out how many calories, and notice that these are calories with an uppercase C, are obtained from a pat of butter if it provides 150 joules of energy when metabolized. So how are we going to solve this problem? Well, we're going to have to convert from joules into calories using this equality here. And then we're going to have to convert from calories with a little c over here into calories with a big C, food calories, because that's what the problem asks for. So we have our 150 joules. We're going to cancel that out with our 1 calorie per 4.184 joules. And they actually made a little mistake here when they made this slide. That should be exact because they mentioned the previous slide this is exact. But either way, it won't affect our answer sig figs. We're limited by the 2 sig figs in our starting value here. And so we end up with 36 of these little calories. So now converting these into food calories, we're going to take our 36 calories, divide them by 1,000 calories with our lowercase c per every 1 food calorie, and that's going to give us 0.036 calories. And again, we're restricted to 2 sig figs by our starting value. So that's a pretty small number. That's a really tiny little bit of butter right there. Butter is actually very calorie rich, so you know that's a really small amount. So what I'd like you to do now is pause the video and complete questions 2 and 3. All right, let's move on to talk about specific heat. So specific heat is a quantity that varies from substance to substance, and it expresses how much energy must be added or removed in order to change the temperature. And we used it in this equation below, heat, which is a type of energy. So energy is going to equal our specific heat for our given compound times our mass times our change in temperature. And our specific heat will sometimes be expressed in joules per gram degree C, and it can also be expressed in calories per gram degree C. But notice our mass is going to be in grams, and our temperature is going to be in degrees C typically. So this is just a table of some specific heats for various elements and compounds. You can use this as to look up these values for solving problems. But I want to point out water. Water is of kind of particular significance here. Water actually has one of the highest specific heats of almost any compound out there. Very large value here. So that means water is very resistant to temperature change. Or in other words, we have to add a lot of energy to heat water up or remove a lot of energy to cool water off. That means that water tends to stay pretty stable temperature-wise. And this is actually kind of important. This is what provides us with our temperate climate in Seattle, because all that energy that'd be required to change the temperature of the Pacific Ocean kind of buffers our temperature here. Or similarly, our bodies are primarily water, so it keeps our body temperature nice and stable, that water is so resistant to temperature change. So we have an example problem here. How many kilojoules are needed to raise the temperature of 325 grams of water from 15 degrees C to 77 degrees C? So how are we going to solve this problem? Well, first thing we have to do is find our delta T. So we're going to take our final temperature, which is the 77.0, minus our initial temperature to get 62 degrees C. And so I want to point out that if our temperature is going up, our delta T should be positive. And if our temperature is going down, we'll actually see a negative delta T right here. So temperature up, positive delta T. Temperature down, negative delta T, which kind of makes sense. Delta means our change. And so we're going to take our equation here. Heat equals our mass times our delta T times our specific heat. They would just rearrange the order of these, but that won't affect our answer. And now if we plunk in our values here, 325 grams times our delta T, 62.0 degrees C, times our specific heat in joules for water, 4.184 joules per gram degrees C. Again, if we have a different compound, we're going to have a different value right here. This is just the value for water. And then finally, the problem asks for kilojoules. So we're going to use our kilojoules conversion here, 1,000 joules per every 1 kilojoule, to give us our answer. And notice that all our units cancel out nicely. We end up with 84.3 kilojoules of energy has to be added in order to cause that temperature increase. So I'd like you to now pause the video and complete questions 4 and 5. Our last topic is going to be energy and nutrition. So energy on food labels in the US is usually shown in calories. So these large calories, food calories, these equal 1,000 of our little calories here, or 1 kilocalorie. 1 calorie also with a uppercase C, 1 food calorie equals 4,184 joules, or it equals 4.184 kilojoules. So this is just the same value in different energy units. So when we want to calculate our calories in a piece of food, it helps if we know what components are in the food. We call these three things macronutrients. So our three macronutrients are carbohydrates, fat, and protein, and they exist in food in large amount. So carbohydrates have 4.184 food calories per gram, fat has 8.8 food calories per gram, and protein has 4.1 food calories per gram. And so if we look at an example problem here, a cup of whole milk contains 12 grams of carbohydrates, 9 grams of fat, and 9 grams of protein. How many kilocalories or food calories does this cup of milk contain? So plugging in our values here and setting up some unit cancellations, our 12 grams of carbohydrates times 1 gram of carbohydrates equating to 4.1 food calories here. So we're going to do our unit cancellation. We end up with 49 food calories from carbohydrates. Doing the same thing for fat, but now we have a value of 8.8 calories per 1 gram of fat. Setting up our unit cancellation, we end up with 79 food calories of fat. And then finally, with our protein, again, using our conversion, we end up with 37 food calories of energy from the protein. Summing these all together, that means that our sample of milk has 165 food calories. And you might be a little confused about sig figs here. It's a bit tricky. So each of these was known to 2 sig figs, but when we add them together, this is known to 0 decimal places, 0 decimal places, 0 decimal places. We maintain 0 decimal places, but we actually end up going up to 3 sig figs, and that's okay. That's correct here. So I'd like you to pause the video and now complete question number 6. Once you've completed question number 6, then please go to the discussion board and participate there with your team.